Okay, so you're watching this video, presumably because I'm in another meeting this morning. So I didn't want to lose any more time, so I figured I'd record the lesson. I wanted to generate these kinematics equations I was talking about. I've been talking about the last little while. So far we've been talking about two types of motion. This one is uniform motion. Meaning that it's got a constant velocity. And we know that it's got that constant velocity because we talked about the slope of this position time curve. If the slope is constant, then the velocity is constant. And when we have that, we talk about the velocity. That's a horrible V. The velocity is the change in position, or that we call displacement. So displacement over time. And so when we calculate this, we take position 2 minus position 1, all over the second time minus the first time. So that we'd be looking at, here's position 2 and time 2. That's the coordinates of this graph here. And this one would be time 1 and position 1. And so we get that, that's how we would work that off of the graph. When we get to something where the velocity is changing, as long as we've got constant acceleration, this is non-uniform motion, but it is constant acceleration. And we defined acceleration the other day. Sorry, I'm running out of space there. We defined acceleration. And so this acceleration we said was a change in velocity divided by a change in time. For what it's worth, acceleration is always a vector. It can't not be a vector. So we can't get a vector from non-vectors. So we have to always consider velocity, change in velocity, and acceleration. Velocity is a vector, but if we get rid of directional information, then this just becomes speed. If we get rid of the vectors, we could say that v, without the vector notation, is just a distance traveled over a period of time. So this is a scalar quantity. These are scalar quantities, but for the most part we'll consider the vectors. A couple of things that we notice here is that because the velocity is not changing, so if I had if contrary to the non-uniform motion, I have a v1 and a v2, so the delta is a change, so the final velocity minus the initial velocity divided by the change in time that occurs at. So this slope here, that's our v1, and the slope here is our v2. And of course that happens at t1, or t2, and at t1. And so when we get the v2 and v1, t2 and t1, we can take that difference and the rate that happens at. A couple of things to note that, of course, we said this is non-uniform motion. As long as the acceleration is constant, if my acceleration is positive or greater than 0, this means that the object is speeding up, right? And what that means is my v2 is greater than my v1. And likewise, if my acceleration, or contrary to this, I guess, if my acceleration is less than 0, this means I'm slowing down. Which means my v2 is less than my v1. So I finished with a lower speed than I started with. I'm slowing down, my acceleration is 0. We don't call it deceleration, we call it a negative acceleration in physics. In English you might say deceleration. Just so we complete the picture, if my acceleration is 0, that means this is uniform motion, and that means my v2 is equal to my v1, so there's no change. And then in this case, I'm looking at this situation here. And there's one last case to consider where the change in speed might not, there might not be any change in speed, so v is constant, but the direction changes. In this case, there is an acceleration, and we're going to look at this in the 4U course. So we'll deal with that later. But that's something to consider for next year. So what I want to do now is, I'm going to end this video. Now I'll continue on. I'm going to go down to the next page here. We want to consider the case where when we go from starting from rest and we start to speed up, that's a sort of not quite a trivial case, but it's something that we're kind of used to. What I want to consider is if I start from a v1 at t1 and I go to a v2 at t2, then the slope, just like we get, just as we said, so the slope of the position time curve provides us velocity. And likewise the slope, because it's a rate, since velocity is a rate of change of the position over the change of time, it's the slope of that curve. Likewise, the slope of a velocity time curve gives us acceleration, because acceleration is that change in velocity over change in time. Again, getting it from the graph. Sorry, that's the slope of the curve there, of the line. And again, the only case we're going to consider is when. So I'm just make a point of noting this. We will only consider uniform acceleration. Okay. If we have a change in acceleration, is referred to as jerk, and nobody wants to learn about jerks. That's all you'll need to know, is you need to know that term, just so we're not you know what it is, but we won't study it in any real detail. What we will concentrate on is how to analyze, and what I'm going to do is I'm going to develop a set of equations. It's going to be 5 equations. There can be any, these can be in any sort of form, but what I'm going to stick to is the ones that you'll typically find in our textbooks. So the first thing I want to look at is this. If I have a delta V, if there's a delta V, what that means is I have a V2 and a V1. These are two vectors, but they're different. So V2 is not equal to V1. If they were equal, then I've got no change, and I'm talking about uniform motion. But if they're not equal, this is the case that I want to consider. Well, if I change linearly, if I change moving from here up to here, so if I change from, this is V1 up to V2, sorry, it's already on the diagram, so it's not. So if I change from V1 up to V2, and it changes in a linear fashion, then what I can say is the average velocity is going to be, just like you would calculate the average mark, would be V1 plus V2 all over 2. Oops. So that's going to be the average velocity. I'm going to call this equation A. It's not a final equation that I want, but we want to understand that. But we also know that the average velocity will be will give or can be also derived from the displacement over the time, over the course of the trip. So if the if this is true, then I can say that the delta d, rearrange this, is equal to the v, the average velocity, times the time. But that average velocity is just v1 plus v2 over 2. I want to make sure I've got some room here. I think I'm running out of space. No, sorry about that. The system is running a bit slow. So it's the average velocity times time, but I know that this average velocity is just half of the sum of those two. So v1 plus v2 over 2. Another way I can write that is I can say this is 1/2. Let me move this down a bit. So the delta d, the displacement, is going to be 1/2 times v1 plus v2, the sum of those two velocities, times the change in time. And this is going to be our first equation that we're going to use. This will be one of the sort of what we call the kinematics equations. So that's the first one. There's going to be a total of 5, and we're going to get there. What I'm going to do is, because this video is getting a little long, I worry about it saving up to YouTube. So I'm going to stop this at equation 1, and I'll do a new video for each equation. So here's equation 1. We're going to save it.